this started early this year as an hackathon workshop, the Helmholtz Hackathon Workshop organized at the Jülich Supercomputing Center, and with whom we are also quite actively collaborating within this eco-European project. And also we, as you correctly mentioned before, we started a good collaboration with people that mentor there and working at the NVIDIA Application Lab at Jülich. So we keep good interaction with them for consulting and things like that. Most of the work that I will show has been actually done by a student of mine at the University of Tor Vergata. So actually what non-equilibrium Green's function is all about, I will be very quick on, say, the physical stuff. Basically, it's a rigorous formalism to treat many-body non-equilibrium quantum system. So it is clearly targeted at the electronic devices, but not necessarily only for electronic devices. Actually, a long time ago, some years ago, actually, we started together with the University of Tor Vergata this libNEGF, a general purpose library to interface different representation of the Hamiltonian that can be for devices, finite element or empirical type binding, can be semi-empirical type binding, can be DFT, different representation. So a general purpose library behind and with the ability of driving different type of calculations. It is computationally intensive because it's basically dense matrix complex algebra that I will show you. And one objective of this ECO project is actually to bring quantum computing stuff to exascale. So also libNEGF was selected for bringing such a code to exascale, and this is this initiative that we call NextGF. So I will be talking basically about libNEGF, that is the state of the art of what was before, but of course we are in the transition to this NextGF library. Now libNEGF basically partition the system like a wire, where we have to compute transport along this one-dimensional direction, if you want. It partitioned it into layers, and the Hamiltonian looks like block tridiagonal. And these blocks are dense. Typically depends on the size of the cross section of the device, let's say. The contact self-energies, I don't know if you see my pointer. I mean, the semi-infinite leads are mapped into the, say, the central part with appropriate self-energies. These E and K are energy and K, the K parallel here. And the interactions that I will not be talking about a lot, actually not at all, because it's still work in progress for the GPU porting. So basically we have to do two things. Solve the Dyson equation that basically is an inversion of this matrix, and then a Keldysh equation that accounts for the statistics of the electrons. In the libNEGF, we have essentially an iterative or recursive algorithm that, thanks to some recursive relationships between blocks, allows you to navigate across the matrix and compute the blocks that you need, either on the fly or just compute the tridiagonal blocks that are typically needed for the final output. On the CPU, we use the standard modern Fortran implementation to handle the complex data structure, and we relied all the time to the MKL, basically the Intel MKL library, because it's quite performing for the BLAS LAPAC, for this linear algebra stuff. So the new work is to port essentially this linear stuff to GPUs via OpenACC. I will also talk on one slide about CUDA, and we will rely on cuBLAS cuSolver. The library is parallelized. I said that it depends on energy and K points, and these energy and K points are used to parallelize, to distribute over a two-dimensional Cartesian grid. So the natural MPI distribution is over this. Now we are starting to think how to add a third dimension, that is also the domain decomposition. So a third dimension in this MPI distribution. At task level, so on a single node, we work also with an hybrid OpenMP MPI scheme. Clearly, as far as we neglect interaction, the library, the calculation are fairly energy and K independent, apart from some gathering of data at the end. The interaction brings a lot of communication between nodes because they are typically non-local, but I will not be talking about that now. Without this interaction, the algorithm, say, scales pretty well on a large number of nodes and cores. The first thing that we ported to GPU is this so-called decimation algorithm to calculate the contact self-energy. This decimation algorithm is a nice recursive algorithm that at every iteration remove one layer, if you want, of the semi-infinite contact and renormalizes the interaction and the on-site blocks according to this formula. So again, we have inversion and matrix-matrix multiplication. All these are these block matrices, complex, dense. And all this is implemented in a single subroutine, so it calls for a simple OpenACC implementation. I don't go through the detail, but clearly the OpenACC, I will show you later on basically what we are doing. Just jumping on some profiling, because this was quite exciting and surprising from the very beginning, comparing to these Intel Xeon Platinum that are basically the cluster ULIC nodes and the Ampere 100, and using NV Fortran 21.3, already we get a very good speed up on the simple decimation algorithm. Clearly, increasing the size of the cross-section, we get better because we are more intensive numerically, and from a factor of 30 speed up from comparing single precision CPU versus GPU, we have already factor of 30 up to 100 of speed up. And when we activate the Tensor core, this jumps up to 100 to 400. So very, very surprising when we apply to TensorFlow. And indeed, we reach peak performance that can go up to 90 teraflop, where flops are now TensorFlow. This is quite good. If we look at, if we have an insight on the performance, actually the most important part, I think, is the data transfer. Of course, data transfer is short compared to the algorithmic part. This is just one of the iterations of this decimation algorithm. You see the matrix-matrix multiplication, the inversion. Already here we see it's very good because the transfer of the matrices doesn't virtually take nothing compared to the computation. If we look more carefully, okay, but what is the performance of this data transfer? We see that the data are transferred in chunks. So these are large matrices transferred in 16 megabyte chunks. I don't know exactly why this is occurring, but according to the profiler, we get throughput of about 20-25 gigabyte per second, which is a bit lower than the theoretical roof performance of the PCI Express, but it's still okay. Unfortunately, the bunching reduces by about 50% the performance, but it's still quite reasonable for our purposes. And of course, the main message is that data copies goes as n squared. All the matrix algebra, inversion, multiplication go basically as n cubed. So clearly for large matrices, we get a winning strategy. Going a little bit more in the detail of the implementation, our dense matrices are already wrapped in derived types. I'm talking about Fortran, and they are wrapped in derived types. I didn't write all the other, but the main thing is this. The reason is that we are symmetric also with sparse and CSR matrices. So it was more or less simple and quite nice, actually, of OpenACC, the possibility to wrap OpenACC Pragma with subroutines. where we can basically explicitly and manually copy to GPU data or update copy basically from GPU to CPU data. So at the moment, we didn't use more recent features like deep copy or managed memory, virtual memory things, because we thought that for good performance, we need to have a look and move the data when needed and the data really needed. With the same strategy, we also wrapped around the linear algebra calls. The main one are matrix inversion and multiplication. Again, thanks to the OpenACC data create, data present, we can spread things around different portion of the code, because of course the algorithm is scattered into several subroutines. It's not just one single kernel. We didn't use a lot of kernels. Practically only one at the moment that is initializing the identity matrix on the right-hand side for the linear stuff. Of course, at the moment, the implementations are basically single precision and double precision, and we are not playing a lot yet with mixed precision. So, for an example, the iterative algorithm is performing a lot of things. For instance, a matrix multiplication like that explicitly goes through creating the temporary matrices, where create all wraps create on the CPU, say, and the GPU. Then I manually copy to GPU what is needed, performing the matrix multiplication, and then deleting what is probably what is not needed later on. And so on and so forth. So we have an explicit memory management. So in this way, we ported completely the library, all the features, basically the entire library, to double precision. At the moment, the single precision still has some small issues, but we are working on that. So the next few slides are discussing the performance of the double precision, which are obviously smaller than or lower than the single precision. For instance, we compare fairly with, again, with the Intel Xeon, that still with MKL, and the best performance apparently was reached here with 24 threads per node. And also the comparison is done with one single MPI task per node. And this was done especially to fit the larger structures that are big memory demanding. So we see that we have a speed up of above 10 on double precision, the same decimation algorithm. This should be compared with the speed factor of more than 100 in single precision. If we look at an entire calculation, like the ballistic transmission from one side to the other of the device, we do have some loss of performance, mainly because, well, this is a bit less computing intensive. We have to copy more matrices back and forth to allow the largest matrices. And the speed up goes a bit down to roughly a factor of 5 up to maybe 7.5 on the largest matrices we managed to test, which is okay for the double precision. So this obviously calls for the single precision compilation that we are doing. And this is important for the ECO project, this, let's say, scaling or bringing towards exascale the code. And the idea is, of course, based on the performance on the Tensor core and the number of K-point energy points, we can immediately project the larger structure should already reach something like 270 petaflops peak performance already on the current Joule booster equipped with the GPUs. Of course, in the following the next pre-exascale and exascale machine, we can probably reach higher performance. Just a brief mention, if I have, this is basically the last slide. CUDA implementation, it was mentioned before. I mean, that OpenACC has several advantages in the development speed, but can have some issues, especially then we are developing a library that should be general purpose and should possibly interface with different codes. And we don't want to have too much dependency on the PGI NVIDIA Fortran. For instance, we are coupling with the use of module to DFTB plus, and using PGI or NVIDIA Fortran compiler, this triggers the dependency chain to the entire project. And that can be problematic sometimes because we had to adjust several things in the calling code, DFTB plus, in order to compile. Still some modules don't compile, but okay, we can survive without that. So the idea was to have also a CUDA implementation that offer also large range of features, kernel flexibility and optimizations. Of course, saying that into an OpenACC workshop maybe is counterproductive, but just to mention that it was simple, much simpler than I thought at the beginning, because just adding, and thanks to the ISA-C binding and adding the address into the derived type to the GPU, we could practically do a one-to-one mapping of the OpenACC to explicit call to CUDA, lower level. So this, in principle, improved the code, the portability of the code. Indeed, we can compile with any compiler, essentially Fortran and then NVCC, and we are happy. So my conclusion is that we have ported an entire libNEGF to GPU using OpenACC. All the results I showed are with OpenACC. At the moment, with double precision, we have already a speed up of 7.5, but mini-apps shows that single precision, also exploiting Tensor core, could reach a factor of above 100. And we are currently fixing the library to recompile single precision. So thank you for your attention.